to our 2B review session. Let me turn the volume down a little bit. All right. Try that. Okay. So if you had me at a review session before, it'll be really similar. But we're going to do about an hour of general topics and about half an hour of specific questions. So how that'll work is, in a moment, I'll ask you to raise your hand and give me a topic that you'd like me to review. So, whatever, phase diagrams, log, etc. So I'll review it. If I have a particular problem, I can do that as well. And then I'll get to specific questions. So if your question is really due to a specific question because you have a particular thing you can't solve, you probably want to hold that until later. And I'll just do general topics now. That'll be for 11, 12, and 13. You're in my class, you should know I have videos and the reader and stuff like that. What do we want to start with first? Let's do delta U for a second. Delta U, just as a quick review, this is the internal total energy, usually typically said to be a combination of the kinetic and potential energy. This is also the topic of the first law. Q and W are energies that go across a boundary. So there are transfers of energy across a system boundary, adding up to delta U. Delta U can also be written in this form, delta H minus P delta V. This is enthalpy or Q of constant pressure, and this is work. But note, and I just had a great question about this earlier, sometimes you're thinking I should use this equation, but you don't know P and delta V. Remember, if you're given a reaction, use the equation that work is minus delta N RT. T is usually given, R is a constant. Which R would this be? The 8.3145. Why is that? Because of the units. You want a joule for your work unit. And then delta N is the moles of products minus the moles of reactants for what state only? Gas. Yes, this would be for gases only of products minus reactants. Okay, so delta U can be greater than 0 or less than 0. It depends where more work is. But basically, if you have a system here, and overall it's positive, that means the delta U, there's no real delta U transfer of sorts, but it would be a higher in the system minus out, and then negative for going out. So just like Q and W. But really, Q and W are the ones that go across the boundary. Okay? All right, let's go to our next topic. That was nice. Let's do Q of reaction, because I just kind of mentioned it. Q of reaction. Okay, this is the energy of the reaction. And this is ultimately going to be related to delta H. Okay? So, this is the reaction or the potential energy of the reaction. Delta H more specifically is Q at constant pressure. And there's a number of ways to calculate delta H. Yeah, so Q reaction for us will just be a definition. It will lead you, or if you want to find Q reaction, you usually find a delta H. This will lead us actually to the bomb calorimeter problem, so I can give you an illustration of the difference. So for the bomb calorimeter problem, I don't know if I have an example. I'll take a look. But if I don't, I will make up one for you. Did you all want just an example for the bomb calorimeter? Or did you also want the concept? Concept also? Okay. Let me see if I have a practice problem on the bomb calorimeter. I'm not quite sure. I'll just look through this. I don't, so let me make one up. Okay, the bomb calorimeter has a pretty simple setup. So, let's say this is the bomb calorimeter here. Okay? And a reaction occurs in here. Does anybody remember usually what type of reaction?
Combustion.
Combustion. Yeah, there's a combustion reaction here. And they're usually measuring, let's say this is a thermometer, we're measuring the temperature, and there is some C, or heat capacity, of the entire calorimeter. Not by piece, but the entire calorimeter. So the setup is pretty much always this. The sum of the Q's equals 0. And there's a Q of the reaction. Remember that we were just talking about a second ago. Plus, so this Q of reaction here, plus the Q of the calorimeter. So the Q of reaction will end up being minus Q of the calorimeter, because this is set equal to 0. And the calorimeter would be C delta T. So there's no M, Cp delta T, because typically for these problems, the C is given for the calorimeter. And that's the setup. And this will be like typically the first step. The second step would be converting Q of reaction to the desired delta H value. How do you do that? That's usually with some quantity of mass or moles. So typically Q reaction, you'll divide by some multiplier, a mass or a moles here, and that will convert it into the delta H term. So let's do a little example, just a quick example so you can see how that works. But that's it. That's usually your two steps. Moles or mass, yeah. So we did in class a methane example, and so that was mass that we did in class. I don't know if we did a second one. Let's see. And we did a second one the next day where we divided by moles in that case. So you should have seen both in lecture. Okay, so how do you do a sample problem? We would say, well, we did some combustion reaction, let's say with propane, and it combusted, and the temperature increase was 5 degrees C. So the temperature increase because it's combustion, it's exothermic. These are exothermic reactions. And let's say the C for the calorimeter is 10 kilojoules per degree C. Okay? And we did this for, let's say, 2 grams of propane. Okay? So what you can do is say, well, I won't rewrite what I had written on the previous page there, but it's Q reaction turns out to be minus C delta T. And so you go negative 10 kilojoules per degree C times the increase of 5 degrees C. So notice in this case, and not always for a bomb calorimeter, they give you a temperature change. They may give you final and initial, and you just subtract them. But it's pretty common to even get a temperature change. So we get this. Let's do some, for you math savants here, it looks like this is 50 if you get out your calculator, kilojoules. And then, why is this negative, by the way? Exothermic. Okay, then we're really transforming this into a delta H here, where we're going to divide by the 2 grams. Okay, so this will be minus, in this case, 25 kilojoules per gram. And that would be your final answer. Okay, there's one calorimeter. They're usually like this. If you want to see a variant, see the one I did in lecture on the second one I did the day after we covered it, or the lecture after we covered it. And that was the one with the HCl and sodium hydroxide. In that case, we had to determine C because it wasn't given to you. So we actually did the calculation twice. That was the only difference. Otherwise, they're just like this. Okay, next. We just did this double doozy here, bomb. So let's do the Hess's law now. Hess, this one I definitely need to practice on. And I believe I have one. Let us see. Did I do this one in class? Okay, we won't do that one. Let's see, did I do... This one. Need to zoom in so you don't see the answer. Did I do this iron one right here?
No.
I don't think I did that one. Okay. This was actually from an exam. Oh, I hope you didn't see that answer. Okay. It's actually from an exam. This is a pretty typical level question right here. Okay, so how do we do this? Let's get our blank sheet out. Remember, I have 2 steps in my strategy. Let me refer you to the reader so you can see those. And if you have me before in Chem 2A, same strategy we did, simultaneous reactions. This is page 14, solving technique, middle of the page. And as a very quick summary, you compare the overall reaction up above with the simultaneous reactions, and you find something that appears twice, and you make them match. That's step 1 of my strategy. Step 2 is find intermediates and make them cancel. Okay, so those are my 2 steps in my strategy. Let's try that. So step 1, what would be something good to pick from up here? F3O4 appears here, and it looks like only once, so I'll brown underline it. Okay, do I multiply the top reaction, or am I going to multiply reaction 2? 2. Yeah, you never mess with the overall. Don't mess with that one. What am I going to multiply this with? Yeah, a -1/2, which means I multiply this by -1/2. What does that do? I need that F3O4 on the reactant side. That's what the negative does. And 1/2 times 2 of them will make 1, which will match with my top reaction. Okay, next, what's another good compound to pick? How about CO? Terrible compound to pick. Don't pick that one because it appears so much down here. CO2, same reason, it appears too often. Will FeO work? Yes, that'll work. Let's circle that one, purple circle for that. I'm going to multiply this third reaction by what? A -3. That flips it to get it in the products, and I need 3 total, as I have right here. So that'll do it, times -3. And then I've exhausted my step 1 of the solving technique. I go to step 2. What's a good intermediate to pick? Yeah, Fe. How do you know it's not? How do you know it is an intermediate? Yeah, it's not in the overall. Perfect. So Fe, and it appears only twice. That's ideal. And it's in the reaction I need a multiplier for. So it's good, good, good. Okay, let's do a blue box around that one. Remember, this one now it's intermediate. I need it to cancel. What do I multiply the first reaction by? Remember, I can't change reaction 2 or 3. Okay. I felt like 5 different answers, I think. 3/2 I heard from a couple people. Is that the right, what I want to do here? Negative. Okay, let's double check this. I have -3 irons here, right there. And then I have a little bit. Yeah. And I have 3/2 times 2, -3 there. That'll work. So this is times -3/2. Or now you can finally see the answer. And you see, I'm just going to multiply those delta H's by those multipliers there. And you should end up with -45. Again, this I would consider a very normal question. Not super easy for sure, but this is about the level of difficulty you should expect on exam. All right, next. Where did I put my sheets? We're going to go to chapter 12 now. Oh, is there a question? Okay, we're going to go to chapter 12. And I'm going to start off with a density problem. There's one I was saving for you that I have not, that I say that I did not do in class yet. And it's this one here. Okay, get this one out of the way. This is a foot-and-mouth virus. 1. Give me a second to write that down. Okay, I think I'm all ready. Okay, so in this case, they want the molar mass of each foot and mouth virus represented by those polyhedrons there. Okay, and the molar mass, would you expect that for a virus to be a relatively small number or relatively large number? I know the virus is small, but I want to know the molar mass. So, like say, compared to the molar mass of carbon, is it larger or smaller than that number? Significantly larger. Is that okay? It's a biological entity, many atoms. So I'm expecting a pretty large number for my answer, okay, for the molar mass, just so you can think through it a little bit. All right, so let's try this. The radius of this disease is 90 angstroms. I even know the density, that's 2.8 grams. What's cc mean? Cubic centimeter. And I know this is BCC. So how many atoms per unit cell?
2.
Yeah, this is going to be 2 atoms per unit cell. And this has what? A face diagonal or a cube diagonal? It's the cube diagonal. So this is 4r over the square root of 3, or root 3. Okay, so let's try this. Let's find the volume first. The volume is the length cubed, which is 4r. R is 90 over the square root of 3 cubed. But that will be an angstroms cubed. And I want it to match the density units, which is centimeter cubed. So let's do a little conversion here. Equals 4 times 90 angstrom over the square root of 3. And in our conversion here, there's 1 meter is 10 to the 10 angstroms. And then 1 meter is 100 centimeters. And I'm going to cube that. That will get me into centimeters cubed, which is what I want. Let me see if I found that. I did. That turns out to be 9.0 times 10 to the minus 18 centimeters cubed. And it's really centimeters cubed per unit cell. Get this out of the way now. Now let's work on the mass. I'll get a different color for the mass here. The mass is the number of atoms per unit cell, that's 2. And I can change that to moles by basically dividing by Avogadro's number. And then if I multiply by the molar mass, it'll turn into grams, but I don't know the molar mass, that's what they asked me for. So, density is 2.8 grams per centimeter cubed. That equals 2 divided by 6.022 times 10 to the 23rd times molar mass, all divided by 9.0 times 10 to the minus 18 centimeters cubed. If you solve for molar mass using by cross multiplication, I got 7.5 times 10 to the 6th grams per mole, which you can see is a relatively large number. And so that's what we expect for a biological entity. So it matches what we thought. Okay, there we go. Ready to move on? Yes?
Is it okay to just convert the centimeters before you do the calculation? So in the beginning,
What do you want to do?
before we calculate, convert.
Oh yeah, if you want to initially to convert 90 angstroms just to straight up centimeters, you can do that. That's totally fine. You can in fact find angstroms cubed and then you can convert it to centimeters cubed also. That's another way to do it. Totally fine. Whatever makes sense in your head is fine with me. As long as it's logical. Okay. Next. We're rocking here. Let's do the intermolecular forces now. H bond, dot, dot, dot. All right. we have ionic, we have the H bond, we have dipoles, we have London. Remember that the force increases in strength as we go upwards. However, London will get larger and larger as molar mass increases. Every molecule has which one of those four? London. Good. So this translates into helping us with physical properties. As the force increases, so does the boiling point, the viscosity, what's gamma? Surface tension, and the vapor pressure or partial pressure goes down. Okay? So if we know the force and identified it, that helps us figure out its relative physical property. So this is really where you'd want to use these things. So let's see. Let's say I had which force do each of these have? These are two separate ones here. They both have London. You know that because they don't have any of the others. And in fact, somebody asked me about this earlier. You can tell me if this is helpful, but this is how I explained it to them. Let me show you. I just took notes on the back of my reader. You need to find the dominant force. So what I do, I'll tell you what I do. You can tell me if this is helpful. I ask myself, do I see a metal? If I do, it's ionic. Yes. If I don't, go to the right. Then I ask myself about H bonding. Is there a hydrogen with a nitrogen, oxygen, or fluorine? If yes, H bond. If no, then I ask myself, is it asymmetric? If it is, yes, dipole. If it is not, it's only London. Is that helpful? You like that flow? Okay. So that's what goes through my mind. In the case of argon and xenon, all the answers were no. It's none of those things. So I ended up with London. Okay, can I move this? Are you done? Okay, write faster. We have time. No time. Okay, I will come up with examples, I guess, while you're doing that.
Sorry, question?
Yeah, what's up?
What is the right on top of the H bond in asymmetrical? What does it say on top?
That says no.
Oh, right underneath that?
H plus NOF question mark.
Okay.
So this is the definition of H bond. Is there a hydrogen really on an nitrogen, oxygen, fluorine?
Okay.
And if that exists, it will H bond with something else really that has a nitrogen, oxygen, or fluorine.
Okay.
Yeah. It gets a little more complex. We just do the simple version in our class. Okay, can I move this now? Yeah. Okay. I'll add that to the next reader. Okay, and those people will be smarter, I guess. Let's compare this with this. Okay, first find the dominant force. I'll give you a moment. And then we'll do surface tension. So we'll circle the one with the highest surface tension. That's what we're looking for today. All right, dominant force for the one on the left. H bond. Not H bond. Well, it definitely has London, but that's not the dominant. It's dipole. How did we know it's not H bond? That was good. I'm glad I figured this question out. It's the hydrogen is on the carbon, not on the hydrogens. Not on the oxygen, I mean. So the hydrogen needs to be on the oxygen. Okay, so this is dipole. How about this one? That's London. Everything else just is no when you go through the flow chart that I just made. So which one's the stronger force, right or left? Left. So it has to be the higher surface tension. Let's compare this one. Now let's get a little crazy here. That one and this one. Okay, so you know that the one on the left is dipole. What's the one now on the right with the sulfur in the middle? Also dipole. Uh-oh. Now what do? They're both the same. Molar mass tells you that which one has a stronger force, left or right. Right, because this has a higher molar mass. Sulfur, look at the periodic table, higher molar mass than oxygen. So now compared to this one, I'll just rewrite it. And this one, it's which one has a higher surface tension, right or left? Because the molar mass for London, yeah. So even though they both had dipole, London came into effect this time. Okay, do you need more? One more? Okay. Let me write this down and then I'll answer your question. Okay, what was your question? Electronegativities can come up in two places. Where do we compare them? I think what I mentioned in class is for ionic. And so you're comparing, if you have two ionic compounds, you compare the electronegativity. For the one that we just did, you could if that's how you figured out dipoles. But that's not how I taught it last quarter, or if you took me 2 quarters ago. You were last quarter. That's not how I taught it last quarter, so I'm just not using that method. But that is a method if that's how you learned it, you know, when you did dipoles, which is fine. That should work too. Okay, for the next one, dominant force on the left-hand side. Oh wait. You have to ask me a different question.
Well, kind of similar to the one before. Is there one that's opposite? So like decreasing molar mass means separating one?
Did I say that at one point? Does anybody remember? Does decreasing molar mass ever
No, not with
from
dipole.
with something else?
Yeah, like a different.
Did I ever say that in class? I could have, but I don't remember saying that. I don't think so. But we talked about boiling point so many times that there was a lot of like funny things that went with boiling point. Like the atmospheric pressure for the boiling point. We also did the normal boiling point when we did clapper-on. What all did I say about boiling point? There's a lot of funny things with boiling point. So there might be something funny like that I'm not recalling at this moment, but not for this problem. Okay? Yeah. All right, dominant force? Ionic. You see a metal. Here? Well, it has London, but it's not the dominant force. What did you say? Hydrogen bonding. Hydrogen on a nitrogen, right? So, ionic is stronger, so it'll also have the higher surface tension. Yes?
For the second one, how were you able to determine that CH3SH was a dipole?
How do you determine that has a dipole? Yeah, that can be a little bit of a tricky one. Well, how did the rest of you know that? How did you know that these were dipoles? Yeah, they're not symmetric. So they have 2 lone pairs here. You remember Lewis vaguely back in the day? So every oxygen has 2 lone pairs when it has a 0 formal charge. And likewise, it has the pattern. Every nitrogen will have 1 lone pair, oxygen will have 2, fluorine column will have 3 when it has a 0 formal charge. And that means, anybody, what shape is that in the middle? It's bent. Yeah, so it actually, just like water is bent, so for example, this one would look like this. So either, I don't know what the heck everybody else is doing, but if in your mind you are imagining a bent shape because you knew there were 2 lone pairs. So if you're not sure, it's always safest to draw the Lewis structure. Yeah, if you want to try to shortcut that, sometimes you get into trouble if you thought that was symmetric. Then you'd be in trouble. Yeah.
So basically the strongest force will have the strongest surface tension?
That's right.
Okay.
Highest force. Follow the table. It's in your reader, and I also recreated it up here at the top. Gotta follow this pattern right there. Now, I derived this from first principles, so hopefully you know the concept so you don't have to memorize it. Surface tension is, the force is strong, it's going to hold the surface really tight. So it'll have a high surface tension. Okay, let's go on. Phase diagrams. For a phase diagram, you just want to know all the parts, really. So it's all conceptual, there's no calculations with it. Pressure versus temperature. You know there's 3 parts. And definitely look on the practice exams. I have a number of different types of these questions. They're all kind of related though. Okay, this point right here is called, that's the triple point. This is the critical point. Does this line have a critical point?
No.
No, so what happens to it?
It goes on to pressure.
It continues. What happens to this line at the critical point? It ends, that's it, okay? So, let's see. What else did I do on this? Oh, a line that goes horizontal is called?
Isobar.
Isobar, constant pressure, and vertical? Isotherm. My isotherm, if it's going that direction, has undergone what phase change?
Condensation.
All right, really into it here. More excited than I am, I think. Okay, this one has undergone
Sublimation.
sublimation. So know all those phase change names. The Colossus Clapeyron describes this line right here. This is the vapor pressure line right there. So know the isotherm, isobar, all 6 phase changes. And somebody asked me, so we might as well do this now. Delta H, so usually there's like delta H of sublimation, delta H of, say, condensation, vaporization. The only funny one is fusion. This is what phase change? Melting, so that's liquid to, or solid to liquid, okay? So if it goes solid to liquid, is it exo or endothermic?
Endo.
Endo, why? You're putting in energy to melt it. So is it a positive or negative number? Positive. Is that okay? So you want to be able, for any phase change, to know the sign of delta H. So delta H of condensation, let's just do all of them.
Positive.
Delta H of condensation, positive or endothermic, because energy goes in to condense. Is that what you're saying?
Oh, okay.
All right, I will repeat that then. So you're saying it's negative because energy goes out to condense it. Yeah, you're taking energy out, so it condenses, it's getting cooler. So we said negative, right? Sublimation.
Positive.
So you're putting energy in to go from solid to gas. Is that what you're saying?
Yeah.
Okay. Sounds good to me. All right. And that's about it with the phase diagram that I can think of right now. Yeah. Oh, that's awesome. How do you find, well, I don't know if yeah, we might ask you the melting point. I guess that's possible. Okay. How would I find the boiling point? Let's start there. Anybody? That's it. I need to find atmospheric pressure. So once I find atmospheric pressure, I'm good to go. So let's say it was right here. If this is 1 atm, say we're at our atmosphere, then it would be right there. If it was below the triple point, what's going to happen? What if atmospheric pressure was below the triple point? Then what?
No boiling point.
It would not boil. Right? It can't boil if it's down here. Is that okay? What would it do?
Deposition.
No. Not fire. I think you had some Red Bull before you came. Yeah, it would sublime. Right? If it's below, that's the only way to get to the gas phase, from solid to gas. Okay. So the melting point, if this is your line of atmosphere, it would depend on what the melting temperature was, because it happened at different pressures. But if you were atmospheric, then this would have to be the melting point. Wherever that's at. Okay. If you're atmospheric, you have to do that. Okay, next. We just did delta H of fusion. Let's do Closh's Clackerall. Let me write the equation down first. Oh, and you'll be given the equation on exam. Do I need to talk about the equation, or you just want to practice? Practice. Just practice, okay? Just a couple notes. This is a common question where you'll hear the words normal boiling point. What does that tell you? Yeah, this means, hey stupid, okay, maybe they're not coming back. Hey, nice person. Remember we're atmospheric pressure, okay? That's usually the main thing. If you did the homework, there was that benzaldehyde example. And in that example, they were asking for delta H. After you found delta H, then there was a second part to the problem. So that's another problem if you take a look at that benzaldehyde. Typically, though, it would work like this. Let's say I want the vapor pressure, I have a good one, of water at, so let's go 50 degrees C. Okay. I'll give you a second. How do you think you would set it up? Here's the question. Boom. No, I'll give you 10 seconds. You need more time. How would you set this problem up?
Oh, you would know H vapor and vision of what's happening to you. Oh, so you would be finding P1, so you just plug everything into P2.
Okay. What am I missing? I want the vapor pressure of water, that's fine. What else do I need to solve the problem? The temperature is 50. I don't have a second point. So what second point would I use? Yeah, you know that water boils at 100, and you know the pressure would be 1 atm. So you have a freebie point when you know it's water. And we would not want to give that to you because you already know that. And so we don't want to waste ink on the exam. Okay? So, let's say this is P2, what you're solving for here. P2. So T2 would be here, 50 plus 273. Make sure to change it to Kelvin. That's a common mistake. And then you know P1 would be 1 atmosphere. And you know the temperature would be 100. And you add 273 to that as well. So you would just solve for P2. One common thing is people don't know how to move the natural log over. So on your calculator, you would raise this. This would be the, what is it, the argument of this E? Yeah, that's the correct term, the E to this whole power right there. Make sure you can do that on your calculator. If you can't, that is a major problem to fix before the exam. But I would definitely practice calculations like this, at least a couple. Make sure you can do it on your calculator. Yeah. Delta H is on the back of the exam. That's a good question, though. Did I correctly write this as a positive number? Anybody? Yes. Vaporization. Am I putting H in or taking it out? Putting in. And that's positive? Sounds good. Just making sure. You always need to. We don't necessarily give you the right side of the delta H for the phase change. It's just to go one way or the other way. It's that number, but you need to check the sign always. Okay. So we got that. Chapter 13. Let's do N. That's a pretty quick one. Just a little concept we did. if you know molarity, so let's say we have 2.0 molar. And we usually do this for like acids. So let me pick a couple acids for you. So if that's the molarity, and you want to find the normality, it's multiplied by the number of acidic hydrogens that you have. So if it's 2 molar for HCl, it would be 2 normal, because there's 1 acidic hydrogen. But for H2SO4, there's 2 acidic hydrogens, so this would be 4. For H3PO4, there's 3, so 2 times 3 is 6. That's it. Yes?
Are you only going to ask like for a normality of acids and bases?
You could be asked for a base. Yeah, acids or base, that's right, but it would apply in other areas of life as well, in the sciences. But like, let's say sodium hydroxide, 1 hydroxide, that'd be 2. For strontium hydroxide, there's 2 of them, 2 times 2 is 4. Okay? All right, that's normality. Let's do Raoult's law, and let me see if I have an example of this one. I'm not sure. Let me flip over to Raoult's law. I have the one that the sub is going to do with you. I think I will have to make up one. Let me try my best to make up one. Okay. Let's say we have a container of A and B, liquid. Okay, so thus there would be a vapor pressure up here, etc. Okay. And let's say I have for A, there's 1 mole, and for B, let's say there's 3 moles. And let's say that the pure pressure of A is 100 torr, and the pure pressure of B is 200 torr. All right, we're back. So does everybody get this has a higher pure pressure? Does everybody know what pure pressure means now? Pure pressure, just B alone and just A alone. Okay, so let's say I wanted to find P total above here. So what's the total pressure given by A and B together? How do you find that? Well, I know that P total would be the partial pressure of A plus the partial pressure of B. The partial pressure of A is the mole fraction of A times the pure pressure, and you could write the equivalent for B. So see that I need the mole fractions to get this. So to get the mole fractions, the mole fraction of A is the moles of A divided by the total moles, 1 plus 3, or 1/4, or 0.25. The moles of B would be the moles of A divided by the total moles, which is 0.75. And so P total would be PA, the mole fraction of A, 0.75, times the pure pressure of A, 100, plus 0.75 times the pure pressure of B, 200. So just plug it into this equation, partial pressure of A plus partial pressure of B. In our case, this would be 25 plus 0.75 times 200. 0.75 times 200.
Yes.
Okay, 150. So this would be 175. Okay? Now an additional question I could ask you would be, what's the mole fraction of A above the liquid? Remember, these are mole fractions inside the liquid, but I could ask you the mole fraction above the liquid. How do I find that? What law? Dalton's law. That's the partial pressure of A divided by the total pressure. That's Dalton's law. The partial pressure of A, what's that number? Well, I know total pressure. I'll write that down. 175. That's total. What's the partial pressure of A?
100.
25.
Did I find the partial pressure rate? Ish, it's on the page. It's 25. Remember, this is the partial pressure of A. What's the partial pressure of B? 20, it'd be this number. Whatever, 25 by 175. That's 17. Okay, 17. So you can see this number and this number are different numbers. And that's pretty normal. That the mole fraction in the liquid is a different number than the mole fraction above the liquid. Remember, one more time, this is the mole fraction of A above the liquid, or in the gas form. This mole fraction right here of A is in the liquid. Okay, that would be a pretty normal question. Yes?
So above the liquid, the partial pressure is the same as the partial pressure in the liquid?
The partial pressure P of A, the pressure is always of a gas. So when you're finding partial pressure of A, that's always in the gas phase. So the total pressure, always in the gas phase. Pure pressure, always in the gas. Any pressure is always in the gas phase. The only difference is where the mole fraction is.
But for like 25, isn't that inside the liquid?
The 25, that's the partial pressure of A, and that's above the liquid. The mole fraction is in the liquid, but the pressures are always gases. Always, always gases. Is that okay? So it just matters where the mole fraction comes from. And that's the only difference, really, or that's a key difference, I should say, between Raoult's law and Knowles' law. The other difference would be, are you using P total, are you using